Here's a mini lecture for lesson 109. Rational numbers. You guys should know that rational numbers are numbers that can be written as a ratio or as a fraction. Hopefully you know the difference between a rational number and an irrational number. Irrational numbers are the decimals that don't repeat ever, like pi or e or square root 2 or something. But rational numbers can be written as fractions even if they are like repeating decimals. Okay, so there's a way to do that. There's a way to actually write these as fractions. I don't know. There's actually a couple ways to write these as fractions. You might have done this a different way maybe last year, but now that we have, you can't see because of my camera. There we go. Now that we have the geometric series, we can do the sum of the terms of a geometric series. We can kind of use that as an aid to writing these repeating decimals as a fraction. Okay, so you get a little practice using your formula there. So I'm going to kind of I kind of do mine, I guess I sort of do mine the same as they do, but I make mine a lot shorter. So what they're doing, and actually right here, they go ahead and they show you. So if you want to see where this came from or whatever, please read all this if you want to see where it comes from. But basically it turns out that however many digits are repeating, that helps you find R. Like if there's 2 digits repeating, R is going to be 10 to the negative 2. If there's 3 digits that are repeating, R is 10 to the negative 3. And if you look up here, you know, they do all this business right here. That'll help you understand why that works like that. I'm going to go ahead and do one of the problems. It looks like it's number 6. So it says use an infinite geometric series as an aid for expressing 0.00031 repeating as a common fraction. So there it is. There's 2 digits repeating because you know this little bar means it goes 0.00031313131. So since the 2 digits are repeating, then I know R is negative 2, or 10 to the negative 2. And so then this is that formula that helped us find the sum of a geometric series. So you have to put a sub 1 on top and then 1 minus R. Well, we already have R. A sub 1 is just going to be that number, and if that doesn't make sense, go back in your book and read these examples, and they kind of make it make sense how they see right here how they broke the number up into these little pieces that add up to make the repeating decimal. So really you can just use this as a sub 1, and we are. Okay, so put that on top, and then 1 minus 10 to the negative 2, and then we want to actually get, you know, a nice decimal. Well, I don't know how nice it is, but a nice decimal on the top, not scientific notation, just a nice decimal is the way I like to do it. So I refrained from writing that as 10 to the negative 4 or whatever. I didn't write it in decimal scientific notation for a reason, because I like to just scoot my decimals over. It seems a lot easier to me. This one I go 1 minus 10 to the negative 2 is actually just that number. And then if you just put that in your calculator, you get 0.99. And then, you know, you can multiply the top and the bottom of a fraction by any number that you want. I'm going to multiply it by whatever makes my decimal move, 1, 2, 3, 4, 5. So I'm multiplying it by like 10 to the 5 or whatever. I'm going to move this decimal place 5. 1, 2, 3, 4, 5. That gave me my nice whole number. and then I'll multiply this, or move this the same amount of places. 1, 2, 3, 4, 5. That tells me that it's going to have 3 zeros under there, so that's how you do it. Okay, so the R comes from how many decimals are repeating. A sub 1 just comes from your original number. You plug them in the formula, get decimals on the top and bottom, and then clear the decimal out just by moving the decimal place to the right however many times. You have to do the same amount of times on the top as you do the bottom. And that's it.